This is Cosmographia, the Randall Carlson podcast.
All right, welcome back, ladies and gentlemen, to Kosmographia episode
10.
We are the shiny people. And we are here with Brad.
Looking good. Number 10.
The Shiny Brothers.
That's right.
That's right.
We are here with the quiet guy and Randall.
The Brothers of the Shine.
Freshly polished.
That's right. Got my...
For the listeners, you probably need to explain that.
So we've had a couple of YouTube comments that are like, who are those shiny guys? Like, who are the shiny people? And why do they keep telling Randall that the podcast is over? That was like,
yeah, let the guy talk, damn it.
Yeah, let him keep going. And we're like, sorry, Randall told the shiny people to tell him when it's been an hour.
Well, we need to remind him. Randall said, let's try to keep it to an hour, so we'll tell him, but he may go for 2 hours, but at least we're going to bring it up.
That's right. So.
Yeah, I mean, because we are not locked into some set time frame every week. We can,
right.
And if we go anything really, we go beyond an hour, that should be considered a bonus.
Frickin'
right.
bonus. That's right.
That's right. Bonus.
Love it, people. Come on.
That's right.
Yeah. So, Cosmographia episode 9.
10?
We thought we were wrapping up with Atlantis on number 9, but I think we got a little more. What can we add in about that city plan, Randall?
Well, are you sure you're ready for this?
I don't know. You got something else?
Well, I got another couple of little tidbits before we move on, although always this will be in the background because we're basically laying out a body of evidence from episode to episode, and it's all interlinked. Obviously, we can't talk about Atlantis without the Chronostratigraphic context, which is essentially the Younger-Dryas. So I thought that it would be insightful and helpful to probe into the details about the Younger-Dryas a little bit further, because we are looking at sort of the dividing line, the great dividing line in the history of humans on planet Earth.
Yeah.
The 200,000 year plus history of modern humans on Earth has this big dividing line, this big abyss between modern history and prehistory. If we assume, if we're allowed to push modern history back to 8, 9, perhaps 10,000 years, which is becoming more and more feasible, and as long as we don't necessarily restrict the definition of civilization as being the appearance of writing, because that right now tends to be the criteria by which we determine, were these people civilized? Well, they wrote things down, right? That's been more or less the criteria. And at what point do we see people writing things down? Well, 4,000 or 5,000 years ago, generally in that range, give or take. But when do we see people establishing agriculture? When do we see people domesticating animals? When do we see the dispersion of languages? We can take all of that back to the very early Holocene, the first cities that would be part of the historical record, right? We go back to the early Holocene for that, 8,000, 9,000, maybe 10,000 years ago.
Yeah, Jericho.
Now, yeah, then we go just another millennium or two beyond that, and now we're into the big period of flux, the transition zone between literally 2 world ages. Because if we define the previous world, it was a very, very different world than the world we inherited in the Holocene. And so I think one of the objectives of these discussions that we're doing here would be to help shed light and elaborate specifically how different our planet is now from what it was 15 or 20,000 years ago, while modern humans were living on the planet. And you see, we can't really, I mean, we can pick up the artifacts, certainly we can pick up the tools and the debitage and the debris left over from the activities of early prehistoric humans. But I think that's only telling us part of the story, a small part of the story. And in order, I think, to get at the bigger picture, we have to set a context. We have to understand the environment in which the human story is playing out. So to that end, we will spend time going into the details of the Late Pleistocene and the transition between the Pleistocene and the Holocene, which was marked by this rapid disappearance of the great ice sheets and the rapid rising of sea level and the major shifting of ecosystems and biomes around the planet, the collapse of old ecosystems and the rise of new ecosystems. The transition is truly extraordinary, the disappearance of the great megafauna. So what I would like to do, and if this is of interest to the listeners, is go into that, get into the richness of the detail, looking at the animal life, looking at the nature of the global environment, and then being able to talk about what happened to cause these dramatic changes. What happened to this planet that caused it to shift, literally to shift gears so powerfully and dramatically? I mean, think about this, okay? If you took from the Atlantic Ocean to the Pacific Ocean today, and we went in there and we had this gigantic bulldozer, and we were to bulldoze the entire country of Canada from the Atlantic to the Pacific, and I mean every tree down, gone, right? All of the forests that are reaching from Hudson Bay out to the Western Cordillera and beyond to the Pacific Ocean. Boom, we took every tree out. We clear cut, right? That would be a pretty dramatic environmental change, wouldn't you agree?
Yeah.
Sure.
Well, that's exactly what happened, except now we also have to add a mile and a half of ice over that whole landmass, right? And what I'm trying to do is get people to ponder that and try to actually visualize what we're talking about and appreciate what that's implying. It's implying something that nobody's figured out yet, really. Nobody has the answer. That's the thing, and I want to repeat that. Nobody has figured it out. I think there's teams of scientists out there and individual scientists that are, at this point, converging on the answer, and I think that you know, the quest for an answer has been considerably accelerated now that we have expanded our thinking to embrace the cosmic domain. I think now we're going to be able to get somewhere with trying to understand the changes that have engulfed this planet repeatedly, and most especially and most recently 11 or 12,000, 13,000 years ago during this tremendous time of transition. But there's all these other little anomalies that the standard model of history cannot explain. And so one of those is germane to the subject that we've been talking about for the last 4 or 5 episodes. So I think to that end, I will do a share screen, and we'll have a look here back at the circular city complex that we left off with. And let's do our screen share. Here it is. I think you guys are going to like this.
Coming up. There it is.
Here it is. Yeah. So if you recall in the description, the Temple of Poseidon was on this central island. And Plato carefully describes the diameters of these concentric rings that are composed alternatingly of land and sea. And the sea was brought in through this canal. The circular moats were cut, and all of this was to facilitate the passage of the ships, the triremes that are carrying trade, because he describes they've got a whole trade network set up. They've got colonies. We'll have to go back and revisit some of the narrative in the text to get that specifics. I don't think we read that specific part, but essentially that's what he's describing. And so this was the hub of this global trade network, or at least, so we say, Atlantic trade network. We might be a little bit more local, yeah. But let's not rule out. We don't want to limit our thinking.
Right.
Okay. So, anyways, here we go. Here we've got the rings, and if you recall, the island was 5 stadia in diameter. right? And then we had concentric rings of 1, right? Let's see, we got it right here. Okay, so what I want to show you is that this Temple of Poseidon is 1 stadium in length and 1/2 stadium in width. So right there is our double square, our 2-to-1 rectangle. Now, for all the geometricians and mathematicians out there who might be listening, you know that the 2-to-1 rectangle is how you geometrically derive the golden section, the golden ratio, which we can talk about at some point. But it's also found in a lot of architecture, sacred architecture, temple architecture. You know, this double square, this 2-to-1 rectangle. It's the proportions of the king's chamber
right.
Right. It's a 2-to-1 rectangle. So Plato's describing the Temple of Poseidon as a 2-to-1 rectangle, and it's 1 stadium in length and 1/2 stadium in width. Now, you remember we were talking about the stadium. Well, stadium is where we get our word. Our word stadium comes from the Greek stade, which was actually the facility, the stadium that they used to have races and stuff in. You see, and it was generally a track. One track around was 608 feet, or generally rounded off to 600 feet. But if you actually get into the meteorological origins of it, the most common length. In fact, if you pulled up, just like the Encyclopedia Britannica or even the dictionary, I think you would find that a stade is usually defined as 608 feet, which contrasts somewhat with a furlong, which we know specifically has a very precise number, which is 660 feet. But you were looking that up for us last week, Kyle, weren't you? The stade?
Yeah, I looked up the unit, the stadion. I was just reading from Wikipedia. I'm looking up the definition now, and I don't see. Okay, here's Webster.
Yeah, it gave us a range between 610 and like 600 feet or something like that.
We're curious also that's the ice ages, and then the in between are stades and interstades.
Interstadial, yeah, that's right.
Stades and interstades. So you got a link there already.
Good point, Bradley.
I am paying attention.
Yeah, I think you are.
I'm not just shiny.
Okay, here we go. Yeah. So
okay,
this is at dictionary.com.
Okay.
Ancient Greek and Roman unit of length, the Athenian unit being equal to about 607 feet.
Okay, they're giving 607 feet, right? Okay, yeah, you'll get variations on it. Now, to the more in-depth academic studies, you will get something more precise. But actually, the fact that there could be variability built into the stade may be relevant, because the length of the stade may have been adjusted according to local geography.
Yeah, I was going to ask that. Yeah.
Yes, and so we could go
where you were in terms of latitude. Maybe it would adjust.
Yes. Yes, as you go, see, because here's the thing: if you have a minute of arc, a degree of arc, a second of arc around the parallels, the great circular parallels around the planet, obviously, as you're going away from the equator, those circles are shrinking, right?
Yes.
The radius of those circles is shrinking, and so therefore, any increment of the circumference is going to be shrinking with it. Yeah. So if you start out a degree, you can do this. The polar radius of the Earth is very close to 7,900 miles, and the polar diameter, 7,900 miles. Equatorial diameter, 7,926 miles. So you got a 26-mile difference there. Now, there's another way that you could possibly adjust the length of a unit of measurement based upon a changing size of the Earth, is because not only is an arc of the parallel changing, but so is the length of the radius as you go from equator to pole. And in fact, as you go from equator to pole, the length of the radius the Earth's radius is going to shrink by 13 miles. And that kind of came up earlier in one of our discussions, talking about plate movements and so forth, because we've been talking about the idea that we have to be looking at a more dynamic model, in that not only do we have the continental drift movement, the lateral movement of plates, but we've also got the vertical movements of the plates. And that movement those two movements are likely integrated. In other words, as you do this, it probably accelerates this. That would only be natural, see? So anyway, the size and shape of the Earth does play into a number of important things, and has to be considered when we're thinking in terms of the changing planet. Because you see, the idea that the Arctic Circle is where it is, and and compared to the center of mass of the Great Laurentide Ice Sheet, which was centered over Hudson Bay. And a lot of the Arctic Ocean was actually clear during the late glacial maximum, which is pretty bizarre when you think about it. And Western Alaska was, for the most part, not glaciated. Large parts of Siberia were not glaciated. The entire glacier mass would have been shifted off of the North Pole in this bizarre way. Also interesting, if you take the Arctic Circle and the size of the Arctic Circle, and it were you to move the combined Laurentide and Cordilleran ice sheets up into the Arctic Circle, it would pretty much fill the Arctic Circle very nicely, see? So this has led people like Charles Hapgood to speculate, and others to speculate, that there was some kind of a pole shift. Now, earlier, Emanuel Velikovsky theorized a pole shift, but he was looking at the whole axis of the Earth shifting, which could only happen under the most extreme and extraordinary circumstances. And I don't really believe that model. I don't believe this model. Charles Hapgood's model was a little more sophisticated, in that he saw sort of episodes of accelerated plate tectonics where this movement could get accelerated. And if that movement is accelerated, it could lead us to conjecture how much of that movement could occur and what would be driving it, see? And I think that, again, we have to look at this isostatic adjustment that's going on, because if you have a major deglaciation and you have some sections of the Earth rising by 2,000 or 3,000 feet, other sections of the Earth depressing by 2,000 or 3,000 feet. Now what's happening is, because as the planet is spinning, it's essentially a plastic mass. So its mass is going to be trying to distribute itself according to the sum total of these centrifugal and gravitational forces working on it as it's rotating. It never gets there, never gets to equilibrium, but that's what it's trying to do, see? So now you have this major glaciation and deglaciation episode. So now you've got this enormous mass transfer over the surface of the Earth. What does this do, not only to the stability of the Earth's orbit, or rather rotation, not its orbit, its rotation, or the process of plate tectonics? So if you have a deglaciation and part of the continent rises, what has happened there? See, it's like, you have to think of it this way. If you're going from the equator to the North Pole, or vice versa, from an equator to the South Pole, you're basically going downhill, right? If you're going from the pole towards the equator, you're going uphill, and you're going to have climbed a 13-mile hill to get there, see? So now you move one of the plates 2,000 or 3,000 feet away from where it would want it to be, given its latitude. Does that set up an impelling force that would cause that plate to want to move, to migrate to a latitude that would be actually consistent with its distance from the Earth's center of mass? You see what I'm getting at?
Yes,
I do. Yeah.
I'm having a hard time explaining that. But so what I'm getting at is does this motion accelerate this motion?
Right.
And once this motion gets underway, I mean, can it play out? See, I wouldn't go so far as Hapgood did to think that motion would be something that would happen overnight. I would think it would be more over a period of 3,000 or 4,000 or 5,000 years. And in fact, it could still be going on. And this may be one of the reasons why the magnetic pole is oscillating still around the pole of rotation, which it's doing. See, the planet is probably not returned to stability after the chaotic events of the transition of the Younger-Dryas. It's probably still moving there. And we may even go so far as to say that some of the volcanism and the seismicity that we're seeing now still could be dissipating aftershocks, because that's how extreme those changes were 11, 12, 13,000 years ago.
Yeah. I was going to say, like, in line with that, the isostasy motion, especially how drastic it is at the very beginning. If you have a catastrophic melting, then the initial isostasy is going to be drastic, right? It's going to move quickly, and then eventually slows down, right?
Yeah.
That quick isostatic up and down vertical movement of those plates may actually change the plasticity of the low velocity zone in the upper asthenosphere and allow sliding to happen better.
Yes. Yeah. That's certainly, yes. There's nothing implausible about that. Yeah. I would think. So it could be that there was, pole shift. What do we mean by that? Maybe Hapgood's idea of he was looking at the entire outer shell of the Earth, basically loosening at the asthenosphere level and sliding over the mantle. I don't think we have to go that far, and we don't have to go as quick as he did. But I think his basic idea of accelerated plate tectonics may certainly be feasible, and could explain. I mean, he was seeing that was what could have been driving periods of orogenesis. Do you know what I mean by that?
No, I don't.
Orogenesis. What is orogenesis, Kyle?
I'm gonna figure that out.
See, now the problem is,
did I inject that?
What?
Well, I was trying to inject mountain building there.
Oh, is that what it is?
Brad, this was a test for Kyle.
No, it was a test for Google.
I just got to keeping quiet then. Oh, all right. I do have an inside scoop on this for 22 years, so
right. That's kind of the given here, Brad. It's the Shiny brothers that we're trying to get caught up here, get them up to speed.
They're the fresh students. All right, we'll let them run. He's got Google. I don't remember having Google 22 years ago.
I need to go get a paperback dictionary.
Oh,
orogenesis.
Orogenesis is just the process of mountain building, like Brad said. And mountain building is generally considered to be a very slow process because it's being driven by continental drift, right? So continental drift is you have spreading centers, and this goes back to what we've been focusing on for the last 4 or 5 episodes in our discussion of Atlantis. We've had to look somewhat at the geology of the Atlantic Ocean, and we have that the mid-Atlantic spreading center right there. We've got the plates moving away from there. We've got magma upwelling, flowing outwards, solidifying as it moves outwards. And so what we see is that the youngest lavas are closest to the center of the fracture, the big fault line, runs up right through the cuts, slices off a big chunk of the Azores Plateau, which is now several thousand feet under the surface of the sea. But so we've been looking at that, the plate spreading, and where was I going with that? I guess that was it. Yeah, mountain building.
I was going to ask.
Right. Okay, so the process, assuming that it's a few centimeters per year, basically a very slow process.
Right.
Which, suppose within this new model that we're talking about here, what we're looking at now when we measure modern rates, maybe we're only looking at residual rates. Maybe there are periods of time when those rates accelerate. And to determine that, I mean, we'd have to have a very precise dating of a lot of the lavas that came out, because as you get away from the fracture line, the fracture zone there, you're getting more and more, you're getting older, right? Because those are older lavas. But the other side of it is that in places you've got spreading, in other places the plates are colliding, right? So what happens when the plates collide? Well, there you can have uplift, right? Or you can have overthrusting like this, which you see a lot of those incredible overthrust mountains up there in the Canadian Rockies, where one big slab, it might be 3,000 foot thick slab of rock, slides over another one, and you can see it just built up there, one on top of the other, and you can see the strata in the rock are actually tilted, almost like the crust, the lithosphere broke and then buckled up, right? Now, the assumptions are that mountain building can be really no faster than continental drift. So that mountains are only rising at a few centimeters per year, if that. But one reason I think we could perhaps question that is when we look at the status of a lot of the mountains, particularly the Rocky Mountains, the ones I've spent the most time in, but the Sierras, you could look at the Andes. I spent a fair amount of time in the Pyrenees Mountains. You see those, it's the same thing there. I haven't been to the Alps, no. I'm heading there in the morning, but
okay. Let us know. Give us a report.
I'll give you a report. No, but you'll definitely find the same thing there. That whole belt of mountains that basically goes from the Alps over to the Himalayas. That's all. And in fact, the Pyrenees is part of that fold in the crust. Well, here's the thing: as the fold, as the mountain range is rising, basically the higher it gets, the faster the erosional processes are that affect it and want to basically eat it away as it's rising. You see, so what happens is, again, when we're talking about the planet trying to reach equilibrium, you've got high places and you've got low places. It's the transition, the transport of material is obviously taking place from the highlands, the high areas, to the low areas. And so what is happening is, in part of this geomorphic equilibrium that the planet is striving for, is this. This will go down, the material will fill up, and pretty soon you would have what geologists of old referred to as a peneplain, where basically everything is pretty flat. And that's what would happen if you had if you took away all of these plate tectonic processes. And you would have very shallow seas spread over a large part of the earth, more so than now. And the parts, you'd have shallow sea bottoms, and you'd have, land masses that had been weathered away down almost to sea level, right? There have actually been times in Earth history where it appears that was kind of the prevailing condition. But when we look at the landscape, we're not seeing that. We're seeing, when you travel through the Western states, you're seeing these tremendous 8, 9, 10,000 foot, layers of rock that may have been taken millions of years to accumulate, right? But how long did it take them to uplift? See, there's the question. I think that we should be considering that there might be periods of accelerated plate tectonics and periods of accelerated mountain building, because basically it comes down to this, and we should actually devote an episode to this when we start. We can look at these processes of weathering in great detail, how carbonate rocks like limestone weather as compared to, say, granitic rocks, and what happens with the freeze thaw cycle when once the elevation gets high enough that it becomes perpetually cold. Now you have or you have the colder seasonal cycle going to work. Now you can get really rapid weathering away of the rocks. Also, vegetation. Anybody who's been out hiking can see, trees growing out of cracks in rocks, and the roots of the trees going in splitting the rocks. Huge boulders might be split, or bedrock might be split by and then you add in seismic activity, which we know happens all over the world, varying degrees. Obviously, some places are more susceptible than others, but so what I'm getting at here is that, after this long rant, is that the uplifting may sometimes occur much faster, because the rates of weathering are actually, and see, that's it. When you go and you look at, you study you look at the studies on weathering rates and how quickly mountain ranges are wore down. Basically, what would happen is if you didn't have anything countering this effect and you only had the weathering, somewhere between 10 and 20 or 30 million years, we're down to sea level. We've eroded down because, so here's the thing. If everything is only moving at the rate of modern seafloor spreading, that means mountains are only uplifting at the rate of a centimeter or two a year. But if that's the case, then the uplift is really no faster than the wearing down of the weathering processes. You see, that's what I'm getting at. After all of this, that's what I'm trying to get at, is that the uplifting processes must be a lot quicker than the wearing down processes to end up with the mountain ranges that we see in the world today.
Right.
Or you'd end up with that peneplain.
Or you'd end up with that peneplain, right.
You look at the Rockies and then you look at the Appalachians and you can see, to me, it seems like the Rockies are pointy and sharp, jagged.
Yeah.
Very.
Well, they're much, much younger, obviously. So,
very much, but
the Appalachians were once the scale of the Himalayas.
Right. Yeah. I'm just saying that it seems like you with millions of years of weathering, you shouldn't have sharp, jagged, blocky looking.
Right. And that's the thing too. The weathering is always going to attack the sharper corners, the angular edges first. And what it's going to be doing is it's going to start and it's going to be rounding those off. Right. And it'll continue to round. And what you're going to end up with is a very different look. And you can see places where it looks like that, but you also see places where, man, it looks like it got broken, a few centuries ago.
Yeah.
Oh yeah.
Yeah.
I mean, it's so fresh looking. And then, you get to the, the erosional features in the Southwest, like Monument Valley. And you have these pinnacle rocks, that are, tall, skinny rocks, that is friable sandstone. And how long have they been there? I mean, we know that those areas around there have had seismic activity. There's all kinds of evidence of volcanism up there north of Flagstaff. So there's definitely been tectonic activity. How much tectonic activity would it take to topple these fragile spires of rock that you see in the Garden of the Gods or the Valley of the Gods and and Monument Valley and places like that?
Right. Not much, it seems like. Yeah.
Not much. No, that's the thing. So then you have to say, well, is that an implication that these things are not really that old?
Right.
And you want to see a lot of, excuse me, Randall, just what you're describing. I mean, I read so many comments of people that are going out and getting in the field and going and make trips to see what you tell them about and being able to divine it newly for themselves and see these things. So I want to highly recommend the Icefields Parkway in British Columbia, which runs south out of Jasper National Park.
Yes,
and it is just a freaking geologic wonderland, and you will just be stunned in all directions. Our buddy Ed Nightingale, 360 degrees of wow. Icefields Parkway, south out of Jasper Park. Definitely put that high on your list, people.
Cool.
Yeah. Yeah, we actually added that to our lexicon of geological terms.
Absolutely.
360 degrees of wow.
Yeah, that's a good one.
I'm sorry, you started off with a good one tonight, and I've been trying to figure out how to punctuate it back in there. But you said, and now I'm going to forget it. But you said the oh crap. Oh well, it's gone now.
Yeah, it's gone. No problem.
Okay, so let's go back and have a look, gentlemen.
It'll come back at the least opportune time, right?
That's right. Yeah.
I've been repeating it to myself for 30 minutes now.
Oh no! Write it down.
It was one of the very first things you said. The chronostratigraphic context.
Yeah. Oh yeah.
To put this in chronostratigraphic context.
Well, yeah.
I was like, oh man, that's awesome. I want to do that.
Yeah. Time, stratigraphy, and context.
Isn't that what we're all here trying to do? To put it all in chronostratigraphic context? I thought that's what we were here for.
I am now that I can say it. But
Okay.
you're leading us. Hit it, Kronos.
Well, the word actually, that's a real word, because when you're looking at strata, there are certain assumptions you make about strata that, for example, older strata are going to be below younger strata. Doesn't that make sense? And that's usually the case. You'll be able to find that particular sequence, but other times that sequence is disrupted. And for example, there are places where the older strata is on top.
Yeah.
Now, how does that happen?
Well, I was just thinking the overthrust you were talking about, you'll end up with young strata on top, you go down, you get to older strata, and then suddenly you get younger strata again.
Yes. Yep.
But you'd have to flip something completely over to get the oldest stuff on top.
Yeah, and obviously an impact will be one thing that'll do that.
Oh, yeah.
An impact of an asteroid will do that.
Yeah.
Layers of rock will go up and come back down. That's what to me is so interesting about that, The Great Day of His Wrath by the artist John Martin, is because without necessarily knowing specifically what the immediate effects of an asteroid impact would actually look like, he created a painting that essentially looks like what that would, and he's showing, in fact, Don Davis, who is an artist who's painted a lot of dinosaurs and Cretaceous pictures, and he's done a series of paintings showing the asteroid impact, and one of the pictures he shows is of the paintings he's done, and we could perhaps find it online and show it, or I've got it in my files, but I'm not going to pull it up tonight. But it shows this, and I actually have John Martin's painting. So after we do this, I'll pull John Martin's painting up because it's in this program I've already got open right here.
Cool.
But so back to, hopefully everybody can see this, back to the city plan of Atlantis.
Yeah, you're still in screen share. We see it.
Good. Okay, so the middle island, 5 stadia, or 5 stades in diameter. Then we've got this ring of water is 1 stade, then 2, then 3, right? So the stade, like I was saying, you find the different lengths of it, but there is one stade that seems to have been used very frequently by the ancient Greeks, and you have to get more deep into the history of Greek metrology to get this usage of the stade of 608 feet. But if we look at this, we can see here how it plays into the geometry. The inner island, 5 stades in diameter. So if the 5 stades are each 608 feet, the total is 3,040 feet. Got that? 3,040 feet is equal to 760 times 4. Now, what's interesting about that number is 760 is almost precisely the distance between the 4 sockets, the sockets that held the socket stones, the cornerstones of the bottom layer of the pyramid were each 760 feet apart. Whereas when you got up onto the so-called socle that was marked by the sockets, and I can show pictures of this to people so they can see what these sockets are, but they're 760 feet. And then also 3,040 feet is a half a nautical mile, right? A nautical mile.
So
sailors is 6,080 feet.
You're saying 3,040 feet is the perimeter of the Great Pyramid with that extended socle.
Yes.
Yeah. Okay.
Yes, that's what I'm saying. And so there's a link right here. The numbers, once you accept the 608 feet of that might have actually been the length that Plato was referring to, then the numbers show. And you can adjust the 608 feet by a little bit, which is perfectly acceptable, and you're still within the range of geometric accuracy. See, because the numbers, you got to remember here in geometry, and we're looking at an idealized template, right? But anything that you create out of the real material world of time and space based upon a blueprint is going to have some fudge factor. It's going to have some deviation in it. You know, you can get the best craftsmen in the world and they will build something, but it won't necessarily be precisely what is shown in the blueprints, you see. And then over time, you're going to get even more deviation because of the vicissitudes of time and what that does to a building or
so
a structure.
I don't want to derail you real quick, but why is the nautical mile different from a mile? What's the deal with that?
Well, okay, that's explained in the next line.
Okay.
What does it say? 3,040 feet times 43,200 equals 24,872.72 miles. So what's that number?
Well, I know the 432. I recognize
that. Right.
Is that 24? I don't know. Is that the circumference? No, I don't know what that is.
Getting real close.
Yeah, 24,872 miles is the circumference of the Earth.
Okay. All right.
Yeah. So what's happening here is you've got a nautical mile, which is part of the geodetic system of the Earth, the way we measure the world according to latitude and longitude.
Okay.
Does that make sense?
No, I've got it. Yeah.
So okay. So try this: 6,080 feet. Right now, or go the other way. All of you guys, anybody listening to this, who, you know, I'm assuming and hoping everybody's got your calculator right at your fingertips.
Calculator.
And if not, I'm going to be checking next episode to make sure everybody's got their calculators. Right. So let's do this. Let's take. Well, look what we've got here. 7,917 miles. Remember now I said that the diameter of the Earth varies between 7,926 and 7,900 miles, right? Give or take. And the thing is even when you're measuring with satellites, that absolute size of the Earth has a little bit of play in it. You know, it's not every time you measure it, it's going to be slightly different. So in all of this, there's a legitimate and allowable fudge factor. Okay, so 7,917 you can picture would be somewhere in the mid-latitude range, right?
Right.
Because if it's 7926 at the equator, 7,900 at the pole, what's halfway between those? Well, 7,913 is about halfway. So, right? So
right. A little bit above halfway.
Yeah. A little bit above halfway. Exactly. So anyways, go 300 and let's try some. Let's go. One of my favorite numbers is 7920, right? Because actually, if you took the Earth and you took the area of the Earth and converted it into a perfect sphere, because we know that the Earth is not perfectly spherical. It's oblate. As it spins, it bulges. That's why that 26-mile difference between equator and pole, right? It's because of that spin. So it's throwing it out, right? So if you take 7,920, what I was getting at is that if you were to take the surface of the Earth, you know, I don't remember the exact number in my head of square miles, but you were to create a sphere that had the same number of square miles in a theoretically perfect sphere,
okay,
that had the same number of square miles as the real actual Earth does in its surface, that sphere would be 7,920 miles in diameter.
Okay.
Okay.
So a perfect.
Got that?
Yeah, got it.
Now that is generally the number that we find encoded, apparently, in various ancient traditions, particularly architectural traditions. So using that, let's just try some numbers here. Go 7920 times pi on your calculator, and you're going to get 24,881.4 miles for a circumference. If you use 7,917.23, then you're going to get the 24,872.72 miles, which if you then divide by 43,200, gets you back to the inner island, which is 5 stades in diameter.
Okay.
So in other words, what I'm trying to get people to understand here is that there's a geodetic link. There's 2 links here that are interesting. One, scale to the Great Pyramid, which could be totally coincidental, right? That's 760 feet, totally coincidental, or the nautical mile. Do this, Kyle. Look up nautical mile there and see what it tells you.
All right.
Instead of just sitting there like you've been doing for the last 5 minutes. Get engaged here, Kyle. Become proactive.
I am engaged.
All right. The nautical mile.
Yeah, I'm brainstorming the this city design is basically, you know.
Yeah, it is. I know.
Got hidden Earth numbers in it.
Yes.
I mean, if it correlates to the Great Pyramid, it's got
hidden Earth numbers in it. Yeah.
So,
nautical mile.
Yeah, 676 feet roughly, or 6,076 feet roughly. Not a
yes. Okay, roughly. So that's 4 feet different than the nautical mile I'm showing here at 6,080 feet.
Right.
Which was more the traditional. Now, before all the various adjustments that have occurred, you know, throughout the 20th century.
Right. By people
to
who
get that level of refinement, it was generally taken as 6,080 feet.
Yeah.
So there you go. And what else does it say? Does it explain how it's derived from the Earth?
It does show a diagram of the. Yeah.
Yes. Historically, it was defined as 1 minute.
Yeah. A unit of length used, here we go. I'm going to go refer to my American Heritage Dictionary. Nautical mile, a unit of length used in sea and air navigation based on the length of 1 minute of arc.
Right.
Of a great circle, especially an international and U.S. unit equal to 1.852 meters or about 6,076 feet. But, of course, you know that great circle is subject to a whole range of modifications depending on where you take it, see? So if you take that great circle at one latitude, it's going to be a little bit different than at another latitude. So that's, again, what I'm talking about. You got a little bit of a fudge factor here, and that's totally legitimate. So basically, what Plato is showing here is that the inner island of 5 stades would be half of a nautical mile or a half minute of arc of the Earth's circumference.
And that's let's see, the pyramid base, like on a side, is a half a second of arc.
What, 1/4 of a second? Or maybe you're right. Yeah, I can't remember.
I think one side is a half second of arc, right? You take 2 sides of the Great Pyramid, you'll get one.
That's right. You're
basically 1 second of arc.
Yes. Yeah. So, okay, I've got down here in my notes, I've got the polar diameter of the Earth, 7,899.988 miles. So, you know, it's fair enough. I rounded it off to 7,900. Equatorial diameter, 7,926.677259 miles. The mean diameter, 7,917 miles. So there we go, right there. The mean diameter, right, times pi gives you the 24,872.72, which we could then assume would be a mean circumference. You divide that by 43,200, and now you have the inner island, which was the dwelling place of the gods, right?
Wow. Yeah, it was.
Again, yep. I mean, that's the same scale that the Great Pyramid's modeling, 43,200.
Yeah.
Yes. And so what's significant about that number? Well, we find it all over, but how do we find it? How would we find that number in everyday use?
In everyday use?
In everyday use. Yeah.
I don't know that.
I don't know. I mean, we use procession every day, but I don't know how.
Well, I know you guys, don't you guys adjust your schedules according to the procession of the equinoxes?
Yeah, we're always
I knew that. Yeah, I figured you did. I mean, I was hoping you did, because clearly if you didn't, I don't know if you'd be.
Yeah, we can't hang out anymore, right?
Yeah, no, that's it. Okay, think about the diurnal cycle. What is the diurnal cycle?
The day and night cycle.
Yeah, the day and night. Okay, so how many hours in the diurnal cycle?
24.
24, based upon transits of the solar disk across the local meridian. So in other words, if we set up that plumb bob and we're looking due south, right, and we're sighting against the plumb line, which could now define our local meridian, right? So now through the course of the cycle, we picture the image of the sun as being a disk with a dot, a hypothetical geometrical point in the middle. When that point transits the local meridian, you count 24 hours. We've taken that unit, that solar cycle, which is based on the Earth's rotation, and we've divided that into 24. So the whole 24-hour cycle is totally based upon this rotational relationship between the Earth and the sun. And you could pinpoint it to an infinitely small measure of time if you wanted to. You know, when is high noon? Well, is it 1 second before? Well, or is it a half second before? Or is it a second after? You see, we get into that Zeno's paradox thing there. But in the real world, you have to define a unit of practical measure, right? Mm-hmm. So in terms of our division of the day, we've gone 2 orders of minuteness. We've taken the hour, we've taken that a 1/24th segment of the diurnal cycle of the Earth's rotation, right? And we have divided that hour into 60 minute parts, right? Yeah. The minutes, minute, got it, right? Now, we've taken each of those minutes and we've subdivided them into a second order of minuteness, you see? Yep. So we've got hours, minutes, seconds, right? Okay, so now an hour is how many minutes? 60. Each second is 60. Each minute is 60 seconds. So there are 60 times 60 seconds in every hour, which you don't have to use your calculator for this. 60 times 60 would be 3,600, right? Now then,
okay,
multiply that by 24 and see what you get. Kyle, are you ready?
3,200.
3,600 times 24, the number of seconds in a day.
Oh, I got it.
Was going to be double.
Yeah,
86,400 seconds in a day.
Isn't that interesting? It's
in itself, right?
It's an order of magnitude smaller than the diameter of the sun in miles also.
It is, but it's double the number of, so it's 86,400.
Right.
So half of that, or 12 hours, would be 43,200 seconds. So now the thing to do is to take it to the next order of magnitude, right, which is the annual cycle. And there will be this starting point within the annual cycle, and we have historically, peoples all over the ancient world chose the vernal equinox as that mark, right? The equinox, when day and night were of equal length. Now, we talk about the day of equinox, but it's not a day. In fact, how long is the actual equinox?
A single point.
Infinitely small.
It's infinitely small, exactly. But again, for purposes of the real world and being able to organize our societies and so on, we've chosen to take that natural organic unit, divide it into 24. Each of those units have been subdivided into 60 parts, 60 minute parts, and those 60 minute parts have been further subdivided into 60 second orders of minuteness. And if we now take that moment, we'll say moment, and we could define it as, say, 1 or 2 seconds if we want to actually give it some duration, rather than trying to take it down to infinitely small next to nothing, right? But we give it some duration. We might give, say, the second. What is the second of equinox? And I think if you went into the tables, you could find actually the time of equinox to the second, right? Mm-hmm. But once we get it to that level of precision, now you have 43,200 seconds of day of light and 43,200 seconds of dark.
Yeah.
Okay.
And that is the moment, the equinoctial moment of cosmic balance in the traditional models of cosmology, see?
That's cool.
So you've got this 43,200 subdivision of our temple framework, our measure of time, see? And the fact that those same numbers are encoded both into space and time was exemplified in the ancient structures, see? And even in the language, see, when you think about time, you think temporal, you think tempo, right? Mm-hmm. Well, when you're manifesting the principles of time into space, into solidity, into 3D, you're building a temple.
Right.
Because the temple is it's like the crystallization of time. And so the numbers that you find embedded into the temple are derivative from the cosmic cycles. And it always begins the closest to our first level of perception, the first thing that we see, which is basically the day-to-day cycle of the sun rising and setting. And then from there we can go to the lunar cycle, and then we go to the annual cycle, and then we go to the next level, which was the great year cycle. See?
That's fascinating.
Yeah.
Isn't it fascinating?
What's up with this? What genius?
Well, see, there we go. So how is it when we begin to look at this stuff? Like, what's the origin of this?
Yeah.
I mean, if you go, yeah, we can give certain Greeks credit. Eratosthenes. Did Eratosthenes discover processional, or did not Eratosthenes, but Hipparchus? Did he discover procession?
Nah.
Or did he learn about it from, and then possibly test it and verify it? But was it completely a spontaneous discovery on his part, or was it part of a tradition that he had access to? See, that's a legitimate question to ask.
Yeah, and who divided the circle into 360, and who just chose 60 divisions 60, and 60 minutes, and
the Sumerians are generally given credit for the first, what's called the sexagesimal division of the Earth's circumference.
Okay.
Or the sexagesimal division, of a circle, right? And in a way, once you begin to understand the nature of numbers, it would sort of make sense that you would use that 60. First of all, because in the simple geometric act of dividing a circle, the radius steps off exactly 6 times around, right? So starting with the 6-fold division of any circle is a natural thing to do, right? But what has happened here is whoever have just combined the 6-fold and the 10-fold, and that's how you come up basically with the right. So you've got you have 6 times 6 raised in order of magnitude, and you've got the 360. But in terms of practical use, that's a great number to use because it's got so many factors. I mean, which means that if you have a circle and you want to come up with the way of cutting the circle into pie slices without having anything left over, the way to maximize the possibilities of how many different ways you could slice the pie, you want large number of factors.
Right.
See, so with 360, when you start thinking about it, you can obviously divide it by 2, by 3, by 4, by 5, by 6, not by 7, but by 8, by 9, by 10. You see, so you've got this large number of factors. So it makes it very useful from the practical standpoint.
You
Right.
can't divide it by that number of days.
That's right.
It makes the weeks all screwed up.
Well, see, that's because of the moon. See, the moon doesn't give us the precision. We have to kind of like make little adjustments. And of course, yeah, I mean, even that's why we have to have leap years, because there's not this perfect synchronicity between, think about how nice would it be if there were 360 days in a year.
Right.
Yeah.
Wouldn't that make life easier?
That would be so much easier. Isn't there a weird, there's an Egyptian myth about adding those days to the year?
Oh yeah, the intercalary days or intercalary days. Not sure how it's pronounced. Yeah, I mean, cultures all over the world would have this the Egyptians
Sacred calendar.
So the sacred calendar, where you would just basically have 5 days where you just
nothing happened.
Nothing happened, right?
But there's that legend that says that Thoth got those days and added into the year by stealing them or from the moon or something. I can't remember exactly how it went. He either gets them from the sun or from the moon and then adds them to the calendar.
Mm-hmm.
I can't remember what reason he did that for, but it was like he played a game and he won and got some light from, was it the moon that he did that too? One of them, and he adds them to the calendar. It was a weird.
Yeah, there is. Oh yeah, I can't remember that.
It's all right.
But it's an interesting story that probably sheds light,
right?
As so many of the old legends and stories and myths do. So there, that's that. That's the.
Well, let me throw something in here, and Randall, you're probably going to have to help me out. But since you brought up the moon, I'll try to make sense of it in here. I'm just so fascinated by how many places that 43,200 comes in. But we know, we talked about this in a previous episode, the radius of the moon is 1,080 miles, right? And we've got all these earthwork structures that have squares that were built 1,080 feet on a side. So you multiply those 1,080 feet times 1,080 feet, you come up with some large number, but then you divide it by the sacred acre, which is 43,200, and you come up with 27 acres. So all these earthwork structures have these squares that are 1,080 feet on a side that are exactly 27 acres of that 43,200 acre.
2772 reversed.
Well, yeah, so it would be fun to do and valuable to actually do address this in our discussions here. The use of these numbers and their appearance in geodesy and temple building and so on. Think of this. Baseball diamond, which is actually not a diamond, is it?
No, square.
It's a square. Yeah. Okay, from the center of home plate to the center of first bases, how many feet?
90, I'm guessing.
90, yes, 90. Okay, and again, from first to second, from second to third, from third back to home plate. So that means that the total distance around, and in baseball, we have to have very precise dimensions and very precise ratios between pitcher's mound and home plate, between, the size of the outfield, how far it is. I mean, think how it would change the game, for example, if you moved first base 5 feet closer or 5 feet farther away.
Yeah.
What would happen? What would happen to the game? You see, it's like those distances are very precisely worked out. And it has to do, again, with it's all derived from the human scale of things, right? Because given how fast a person can run, right? Given how fast somebody can throw the ball, given how far somebody can hit the ball, all of those things interact to make 90 feet the exact, precise, perfect distance. You can't change that without dramatically changing the game and throwing the whole thing off, right? Right? It wouldn't work to have 95 feet from home plate to first base. That wouldn't work.
Get
Sorry,
knocked
guys.
more times. Yeah. That's
Right. Okay, so 90 feet on each side of this square. What's the total perimeter of the square? 4 times 90, right? Feet.
Right.
Yep.
So what's 4 times 90, Kyle?
360.
360. And then there are each of those, that's 360 feet, and each of those feet are composed of 12 inches. And we are talking here about a precision that has to be really literally to the inch. I mean, somebody who's coming out and laying out a professional baseball diamond is not going to deviate by more than an inch, are they? And in fact, if they have even the slightest skill, it'll be precisely on 90 feet. It'll be precisely to the number of inches. And what is the number of inches between the center of home plate and the center of first base? It's going to be 12 times 90, right? So how many inches is the perfect number? 12 times 90. I think Russ is giving a
1,080.
1,080.
Yep.
Yeah, 1,080. Okay, so now 4 times that gives you the perimeter of the baseball diamond.
Yep. It's 4,320.
4320.
Yes, it is.
There it is.
I love baseball.
That's why when you run,
I do too.
when you hit first base, you slide it and kick it. It's
Playoffs underway.
That's right.
And then, of course, how many stitches on a baseball?
Oh, yeah. We did this.
We did this.
108.
108.
Right.
So it's got lunar numbers all over the place. It's got, processional numbers and lunar numbers are all built into the game. Now, was that deliberate, or is it just something that happened because as you're refining these geometries, it just hones in on those dimensions?
That's really interesting.
Because
obviously
that quote about everything is still right in front of us and perfect.
Yeah. Ancient knowledge will again abound and overflow as water upon the earth. The remains of this knowledge are everywhere about us in everyday use and perfect. Yeah.
In everyday use and perfect.
In everyday use.
I love that.
Uh-huh.
Where did that come from?
Oh, that's out of theosophical stuff. You've ever heard of theosophy? Madame Blavatsky.
Blavatsky.
Do that quote again, Randall. That's awesome.
What quote are we talking about?
That one you just rattled out.
I'm sorry.
Yeah, no, we got it.
The ancient knowledge will again abound and overflow as water upon the earth. The remains of this knowledge are everywhere about us in everyday use and perfect. The revival of this knowledge will goes on. We'll save that for another time.
Yeah.
But it does say that it'll point to a period prior to the shall we say the dispersion of languages.
Before the confusion of lip.
So
before the confusion of lip, yes, it refers to a time before the confusion of lip, which has always suggested to me that it's implying that geometry is a universal language and that anybody, no matter where, who picked up a compass could figure out that it's natural to divide a circle into 6 parts.
So because these numbers end up being represented in just like small things like a baseball diamond, this human endeavor, and also they show up in incredible works like the Great Pyramid, or if that mythical city ever existed, cathedrals and temples everywhere. Do you think that they also show up in terms of, catastrophe, these larger cycles of the earth?
Mm-hmm.
Same number.
Let's take the number we just that we just derived from the distance around the baseball diamond, 4,320, right?
Right.
What's 6 times that number?
Don't know.
We were talking again about the division of a circle naturally into a sixth, right?
25920.
25920, yes. And what is that?
There's
There's your processional cycle. So 6 times 4,320 is 25,920. Now, what is the actual processional cycle? Well, it may be a little more, maybe a little less, and it's probably, according to current rates, it would be a little bit less than that. But I don't think anybody's going to state with absolute certainty that the present rate has been consistent through a full cycle, and it probably isn't. There might be times when it speeds up a little, times when it slows down. We don't know that the average isn't precisely 25,920 years.
Yeah, the mean.
But it's the same problem with trying to measure the Earth, is that, you know, we're trying to say, well, how many miles is it? Well, it's always changing too.
It's changing, yeah.
It's moving.
Yeah, that's the whole point right there, is because it's the difference between the idealized template of creation and the real world that we inhabit.
Yeah. Well, why would there be recurring things in a processional cycle if this is just a little axial rotation? You know, like
right.
what about that causes catastrophe? Well, unless it's something actually bigger happening.
Russell, I would say that you have to remember that correlation is not causation.
Okay, yeah.
You keep that in mind.
Didn't you study economics?
Wait, well, I mean, I was just continuing your question. That are these numbers continued into?
No, look at it this way. You know, if you you go to sleep, do you ever use an alarm clock?
No,
I don't either. But
I hate those things.
I hate them too. But sometimes I did. In fact, I set my timer on my phone tonight. Otherwise, I'd probably still be asleep on the couch. So I actually set my timer on my phone for 1 hour, snoozed out for that hour.
Yeah.
So think about this. You got the clock on the wall. The clock on the wall is just showing you the timing of things. You know, typically, you know that, okay, sun's going to rise around 6 o'clock. High noon, time to eat lunch. 6 o'clock, time to eat dinner. Midnight, you're in bed sleeping, right? Your day-to-day routine is governed by this cycle more than anything else, right? The day-night cycle.
Yes.
Right? So you're already immersed in this thing, and where was I going with that?
Like you're correlating that to the larger cycles, basically. Like we have this enormous cycle, and that also has it affects the whole biosphere.
Yeah. So the point I guess I'm trying to make is that the clock on the wall isn't causing anything to happen.
Oh man.
Yeah.
I got to stop blaming that clock.
Yeah, it's not
shouting at the clock.
See, yeah, unless of course the clock, you know, has the alarm. Think of that as a catastrophe. You're sound asleep, you know, you're in dreamland, you're having this heavenly dream, and then all of a sudden the alarm clock goes off, and now you have to go through this transition state from one phase state to another. Now you have to wake up and get up. You know, you could kind of look at that as a catastrophe, see?
Yes, yeah.
But the clock isn't really causing it. Well, in a way, it kind of is. Unless you turn the damn thing up. It's not, it's not a perfect analogy, but my point is that, for example, we agreed we're going to get together at 9 o'clock tonight, right? You sent me an email, said log on at 9 o'clock. Now the clock didn't cause that.
Right, that's my fault.
Did it? It's your fault. So we can't blame the clock. We just blame you, Russ.
Right.
Because I would have still been sleeping on the couch. Instead of
I would have called you.
I know that. See, so there, right. So there I had the phone
the
sitting
causation.
next to me. Right.
Yeah.
But that's my point. The processional cycle is not necessarily causing anything.
Okay.
But it may be
the processional wobble might have been caused by whatever thing that was.
Well, and see here, yes, because we do have a real world phenomena, which is the Earth's axis doing this whole processional wobble. Well, primarily, that processional wobble is considered to be a function of the moon. It's of course the sum total of every external force affecting the Earth, but the greatest is the moon. Just as the there are solar tides, but they're not nearly as prominent as lunar tides. So it's the moon is the primary mass that would be doing this, but there are other things. It may see, and here's perhaps the way we need to be thinking about this is when we begin to look at the ratios of the sizes and distances and periodicities of the planetary objects, and then we begin to look at the larger scale periodicities. And we could get into this sometime, because I don't have that material at my fingertips now, but to illustrate it, but to show that with some small adjustments, we can actually bring all of these things into phase. And we see the numbers just popping out. The numbers, all of these numbers. See, like for example, the sun, is it exactly 864,000 miles? Depends on how you measure the thickness of the chromosphere. And I mean, that can vary. I mean, so somebody might want to split hairs and say, oh, the sun is really 865,000 miles. Well, that doesn't really change anything, you see. That is what I'm trying to say, because it's close enough. And we have to understand, I'm trying to get people to understand this idea between an idealized order of things, and which was sort of the Platonic idea, the idea that there is this idealized geometric order. Pythagoras was very much all about that. And then there's the real world, right? And the real world is going to deviate somewhat from the idealized template. And that was the thing you've got. So maybe the extent of the deviation is an extent of the malfunctioning of the whole system, perhaps. My first guess is that in order to look at a correlation between processional cycles and catastrophes, is we have to be looking at exogenic phenomena. We have to be looking at the cosmic domain.
Right. Yeah, I agree with that.
We've got to go there. And at that point, it could be that there is a synchrony going on between, the dance of the planets, the influx of cometary material, the pulse of the sun. All of these things could be related. If the planetary orbits are involved in enhancing the flux of material from the outer zones, the cometary zones, into the sun, and we now are finding evidence that the infall of sun-grazing comets may be a trigger for enhanced solar activity. You see, I think we have to look at this whole thing as an integrated system, is what I'm getting at.
The sun takes about 24, 25 days to rotate on it. So it's close to matching being in these numbers too, even its own.
Right. And then there's the galactic level. We're orbiting the galaxy, and there's been speculation about how our own solar system is kind of doing a sine curve through space, successively crossing the galactic plane. And it could be that when our solar system is crossing the galactic plane, that there is an enhanced possibility. That's purely conjecture, but there may be something to that. Or
that's really happening. It seems like we must be a binary system, because it would actually be doing we'd be going along like this, and so then from the side it would look like we're making a sine wave. Because
well,
it'd be kind of hard to turn the whole solar system back around and make it go the other direction.
Right.
You know what I'm saying?
What's also interesting is every 11 years or so, the sun its magnetic pole flips, and if we're actually going up and down through the galactic plane, we're going up and down into positive galaxy pole, negative galaxy.
That's cool.
Yeah.
Right.
Now, one of the issues that's come up in some of the work that I've looked at over the years would suggest that there was a subgalactic orbital center, almost as if looking at the scaling ratio, say between the moon and the earth and the sun and the galaxy. It's almost like there's a missing level, or missing that would actually kind of unify the whole system. And so there's been conjecture going into some of the work of Gurdjieff, and again some of the Theosophists, I think, and a number of others who have referred to traditions about this, what I would call a subgalactic orbital center. And that would be a fun thing to talk about at some point, which would involve most of the stars, say, that are within 20 to 30 light years, possibly being part of a coherent system, on the part of an orbital system within the galaxy. So there may be, in other words, the point here being that there may be some center around which our solar system is orbiting, which is in turn orbiting the galaxy.
Yeah, that's
but
cool.
at this point, that would only be speculative. But it is not without certain traditions. So that would be something that would be, I think, worthwhile to explore.
I've never looked this up, but do other planets have processional type? Do their axes do this?
Well, yeah, I don't know. I would think they would have to.
Right. It seems like it's part of the physics. Yeah.
It's part of the physics. Yeah.
They're all tilted, so they should have that.
If of course, we're unique with our moon.
That's right. Yeah.
So we are unique with that. And there's another argument, there's another, again, the physics works because you've got the bulge, and it's the lunar gravity that's trying to pull that bulge into its own orbital plane.
Okay. I see that. Yeah.
Yeah.
Yeah. Another way you could look at it too is that it's in reference to the sun mainly, like the idea that our axis is spinning, right? Mm-hmm. Because it's this way on one side of the sun, and then a quarter of the precessional cycle later, it's like that.
Mm-hmm, mm-hmm, mm-hmm.
But if we didn't have the sun to be orbiting around, we wouldn't ever know that would we ever? Yeah, I guess we still would, because the background stars.
Reference the background stars.
Yeah, I mean, we would probably be too cold to be worried about it.
Sure. I'm trying to.
We'd be too busy trying to stay warm.
What I'm really thinking of is that it's almost as though the polar wobble is an orbit in and of itself around the sun, as opposed to we're looking at it in terms of the Earth doing this, but really it's a secondary orbit going around the sun, right? It just
we have to simplify things, but really, I mean, the orbit of the Earth around the sun is defining a helical spiral through space.
Right.
Yeah.
Yeah.
Who flipped Venus over? That's what I want to know.
Well, yeah, because I wish I had my globe right here. I'll try to have it next week. But yeah, if you start spinning a globe like this, let's say in one direction, and then you flip it. Okay, Brad's going to do it for you. He's going to demonstrate.
Yeah, it slows way down.
Say something, Brad.
Okay, turn it back upright again.
All right.
Turn it east to west. Oh, no, not that way. That's the other way. The other way. There we go.
It's mirrorized.
Yeah,
I see. We hold it up a little higher so we can see it. Yeah. Get it spinning good so people can see it spinning. And now flip it upside down. You see that? It's spinning the other direction.
Yeah. That's what
Venus is doing.
That's right.
Yeah. I know.
Hapgood was right.
He was. Who flipped that planet over?
Well, that's what it seems like. Yeah. And Uranus its axis is
like 90 degrees, right?
Yeah. 90 degrees. Yeah. So, isn't that wild?
Neptune has a moon that orbits it retrograde. How did that happen?
That's a whole nother show, at least, right there, isn't it?
We're already over an hour.
I got another show for you. I was just trying to bring this back to the human scale. What you were saying about the deviation off the ideal, right? The golden mean is throughout the human body, right? But everybody's not this perfect phi ratio.
Well, speak for yourself, Brad.
I said everybody's not. Maybe some of you out there, there's
you the Atlas, bro,
right?
Is that the Charles Atlas pose?
Yeah.
I thought that was the sprinter, the Jamaican sprinter, or he's doing a bow and arrow.
Well, I'm sure Charles Atlas didn't originate that, but anybody of my generation, we remember advertisements for Charles Atlas in the back of the comic books.
Yeah.
And my older brother, I guess I was 7 or 8. My older brother ordered it, and so I was doing it for a few months there.
Build your muscles.
Yeah, and that was where the whole the cliche about the bully kicking sand in your face, because remember that was his story. The bully kicked sand in his face, so he decided he was gonna get revenge.
That's right.
So he was gonna make sure that never happened again.
Yeah.
Yeah, a lot of people listening probably aren't going to know who Charles Atlas was.
Right.
So every once in a while, we need to dip back into history.
Google it. So anyway, yeah, that's a whole nother show or more, and the phi ratio within the body and the measurements of us, and then us related to the Earth and the Earth related to the cosmos, and then going the other direction, us related to the atomic level.
Yeah,
we're a nice mean right in between all of that.
So going back to our number. 4,320. What is 3 times that number there, Kyle?
12,960.
12,960. Yes. So that number is half of a number we just found, which was what?
25,920.
Yeah, that's half the precessional cycle. So what that number represents now is the oscillation of the Earth, right, through the maximum deviation of its axis, right. So right now, North Polar axis is pointing to Polaris. 12,960 years ago, it was pointing to Vega.
There you go.
Yeah.
So those are actually two good marker stars in the sky. And Brad and I have done this. We've gone out, when we've been out west, we got the beautiful clear sky and find Vega. And you can now actually trace out the whole processional circle. And that's a pretty impressive thing to do.
Yeah. So
you finally see that, and you can see and realize, okay, there's the North Star, Polaris, but 12,960 years ago it was over there.
So it kind of makes sense that at this time when Atlantis sank into the ocean, they also had a North Star.
Yeah,
because they were seafaring
navigation.
And their North Star would have been Vega.
Right. Yeah. And I've talked about this, that I know that you had told me before that there are ways, obviously, that navigation can be done without that North Star, but to invent navigation without that obvious North Star,
you need a fixed point.
Seems like a much more difficult thing to do. Like it would be more difficult to realize that the stars are making that circle without having that one that's never moving.
Well, it would help. And if you were making observations enough, you would quickly figure out that the stars are doing that. But if you've got a center of that, and Polaris is not really on the center, it's actually a little off. Vega was not exactly on the center, but it's a fairly bright star, so it would have been prominent enough to catch people's attention and to been used as a guide star, a navigational star. And same with Polaris. Now, Polaris has become basically the North Star within the last 500 to 1,000 years.
Right.
As the Earth's processional cycle is swinging around, and it will actually get closer before it starts moving off over the next 2,000 or 3,000 years. It will be moving off.
Vega doesn't ever get quite as close to the center as Polaris does.
Correct.
I've looked at it. Never.
But that is a very odd thing that, why are these catastrophes, if they are on somewhat of a 13,000 year, half a great year cycle, why is it happening when there seems to be a pole star?
Well, see, at this point, we're talking about a catastrophe, but one catastrophe is not enough to
make
a cycle pattern. Yeah.
So,
are you saying the world isn't destroyed every 12,000 years?
Brad, so what are you saying now, that we're right on the cusp of another catastrophe?
Well, I've seen the timeline that goes back 150,000 years. Yeah, so it's pretty consistent.
It is, yeah.
Well, we had our near miss with the was it Chelyabinsk? How do you say
Chelyabinsk?
Chelyabinsk, yeah. Chelyabinsk, I'm not sure.
That could have been it.
Oh, that was a peewee.
Yeah. We survived, guy.
That was a straw shooter. not even an ear flick there.
Yeah, I'm just saying that that was the only crumb that we got this time.
That was all that was left.
We talked a couple weeks ago about one that came by that was a mile, right? And one that came by with a third of a mile satellite. So yeah, those are thumpers.
We survived. That's all I'm saying.
So So we've come up with the number 12,960. Now I'm going to jump back to a meeting of the American Geophysical Union that took place in the fall of 2009, a couple of years after the discovery of impact proxies at the Younger-Dryas Boundary. And I'm sharing screen here, right? Can we see this?
Yep.
Good. Let's see, some of these guys, I know Brad has met some of these guys and been out in the field with them, of these authors. But here's what they're saying. Until the announcements of a possible impact event, Firestone et al. 2007, Kenneth et al. 2009, A and B, at the beginning of the Younger-Dryas, around 12.9 thousand years ago. Right? So look how close that comes to the halfway point of a processional cycle.
Yeah.
Is that coincidence? Well, at this point, I would say, yeah, that's just a coincidence, unless we saw that there were other events that could be tied in with the periodicity of the processional cycle. So anyways, he's saying here that until the announcements of a possible impact event at the beginning of the Younger-Dryas, around 12.9 thousand years ago, the KT impact layer, which is what? The Cretaceous-Tertiary boundary, that resulted from the Chicxulub impact at 65 million years ago, was the only geological boundary layer known to contain coeval peaks in various impact markers, including diamonds. Here, we compare impact markers from the Cretaceous-Tertiary boundary, the Younger-Dryas boundary, and the 1908 Tunguska airburst layer. First-order markers related to impact and biomass burning include magnetic spherules, carbon spherules, nanodiamonds, both cubic and Lonsdaleite. We'll get into more detail on that probably next week. Iridium anomalies, charcoal, fullerenes with high helium-3 to helium-4 ratio, grape-like soot, and widespread extinctions. Observations and analytical data for the Younger-Dryas boundary are consistent with all of the Cretaceous-Tertiary boundary markers, while the last three markers are unknown or inconclusive for the Tunguska layer. Selected markers for cratering events, for example, Chicxulub, are a visible crater, shocked minerals, impact breccia, and microtektites. None of these are known yet, I'll say, for the Younger-Dryas event or Tunguska. So we have not found, or no one has found, shocked minerals or impact breccia. But here's the problem. As we see this, the evidence evolving and the thinking evolving about this Younger-Dryas boundary event, what we're going to see is that it becomes more and more likely that the impacts were into the ice sheet. So remember, we were talking about breccia. When we introduced it, hopefully if somebody's watching these in sequence, they're going to know some of these terminologies so we don't have to constantly define them and redefine them. Breccia was the broken stuff that could come down. I mean, there are numerous ways you can create breccia, but certainly one of the effective ways of breccia is an impact, which breaks up a lot of rock. And then you have basically lots of broken rock. And that's the breccia that it's talking about there that's associated with Chicxulub. Chicxulub, of course, is not visible as a big bowl-shaped crater from the surface, but it is subsurface geophysical exploration is disclosed that it's under a half a mile of limestone on the Yucatan Peninsula, and it's definitely a crater. But so you've got a visible crater, which at this point we don't have, but we have just proposed one as a potential impact site that we think is worthy of further investigation. A visible crater, shocked minerals, particularly quartz, which we will be showing pictures of so people will understand what that means, impact breccia, and microtektites. Remember what microtektites, how they form. It's when the vapor cloud goes up and then begins to descend back to Earth, and as it cools and crystallizes, it takes on a variety of aerodynamic shapes. And those aerodynamic shapes can be spherical, they can be teardrops, they can be dumbbells, they can be cigar-shaped. There's a variety of forms that they can take, I suppose, depending on atmospheric conditions, depending on the chemistry of the objects and so forth. But anyways, microtektites, they're not the kind of tektite you can hold in your hand, but they can be identified under the microscope. So As of this point, a visible crater, shock minerals, impact breccia, and microtektites are not known from the Younger-Dryas Boundary event. So this is what we're going to be talking about over the next couple of episodes here, because I think it's important that people now learn more about this. And there's been recently some, apparently some new evidence found in South Africa that supports the Younger-Dryas boundary impact hypothesis. And there's also some very interesting work taking place in South America that needs to be looked at.
All right.
So I think that it would be worthwhile to spend a couple of episodes just really bringing in a lot of material and educating people about the particular Younger-Dryas boundary events that occurred. Not only the Younger-Dryas at the top at the beginning, but at the end of the Younger-Dryas 1,300 years later. So if you quickly do the math, if you got 12,960 and then minus 3,000 from that, would be the or minus 1,300. I'm sorry, not 12,960 minus the 1,300 gives us 11,660 years, which is within decades of Plato's date, right?
Yeah.
So that is the Younger-Dryas event was a 1,300-year event, lasting from about 12,900 to about 11,600 years. And there's been some new dating that probably brings it in a little less than 12,900, more precise dating. 12,900, a little bit less than 12,900 years ago. But yeah, we'll look at all of that.
All right.
So.
Probably a couple dozen episodes, not just a couple. If we want to take the time to really dig in, there's endless. And yeah, we'll get to the point where we'll have some guests come in. And like we talked about last time, George Howard, good in for the Comet Research Group, and some of the guys just listed on that published paper that you showed there. Yeah, we're gonna get some of those people and have them directly on here talking with us.
Well, I think that's great. Yeah, and yeah, because this is definitely something that when you consider the public discourse these days, I mean, 95% of it is bullshit. Yeah. And, you go online, you go on Facebook, all the stuff, the mainstream media, all the stuff that they're talking about over and over and over, it's mostly all just bullshit. And, there's the really important stuff seems to be getting pushed off to the sidelines, and nobody's paying attention to it. So we're going to try to do our little part here to rectify that by bringing in stuff that's relevant and having fun while we're doing it.
Yeah. Absolutely.
Man, that's we need to cut that out and use that as this is what we're doing on this podcast. What you just said. Just make a little short intro video.
I pulled out some stuff from episode 1 for that exact purpose, but yeah, that was even more concise right there.
Yeah, very concise. I'm like, yep. See all this bullshit? That's not us. Basically is what he's saying.
And I'll throw in here, if people haven't gotten it by now, I'm the guy that does the GeoCosmicReX videos, and I'm responsible for getting these on the channel. So comment away, and appreciate all the subscribers, and keep spreading the good news.
Yeah. Thank you, Quiet Guy.
Yeah.
Behind the scenes guy.
Yeah.
I'm taking notes and getting it all prepared to bring it to you in video form. As I sit here quietly.
Yeah.
Let's be clear on that, because there have been a few comments particularly like the shiny guys,
yeah.
Like, let me say that this is happening because of the 4 people that are right here doing this right now. If you took any of the people out, it wouldn't be happening. You see, this particular thing that, the Serpent brothers are doing their part that makes it happen. Brad's doing his part that makes it happen. And if I didn't have those guys, I'd probably just be doing my design build work and researching and writing and being incognito.
Yeah. People would be wondering, what the hell's Randall up to?
That's right.
Can't do Joe Rogan every month.
Yeah, that's right.
No, but it probably is getting time to do Joe Rogan again, maybe before the year is out.
Yeah.
That's a brew, definitely. Yep, percolating.
Yep.
Yeah, thank you all. You Snake Bros is really making this happen. Being hosts and having the experience and getting it on the podcast. They've been irreplaceable as far as making all this happen. So, joke if you want to. They're integral to this all happening, and we appreciate these guys.
We like to.
I mean, for a couple of stoners, I mean, what? No, that was somebody's take.
Yeah.
And listen, if good questions come in, yeah, we can certainly address those. Some of the stuff, particularly if it's germane to what we're talking about.
Right. Yeah. So we've gotten good emails, and we've gotten some really good emails, and I just want everybody to know we will be addressing some of those really good emails at some point in the future.
Mm-hmm.
So we will do that. And if anybody wants to email us, Kosmographia1618@gmail.com. That's Kosmographia with a K. I'm sure all of you know that at this point. Patreon.com/Randall Carlson. Support the show, support Randall's research, help us get better equipment, help us increase the quality of the show, and also get out in the field and find weird stuff to talk about.
No shortage of that.
That's right.
Yeah, we're headed up to Minnesota, and I'm hoping to get the drone out and get some new footage of the different canyons and gorges that flow into the North Shore of Lake Superior. So that's coming up real soon.
Cool. Yeah, I was also going to say Brad does the GeoCosmicReX site, but he also is the one responsible for all those videos. Like, he actually takes all the equipment out there. When Randall gives his talks, he records everything, sets up microphones, sets up the cameras, runs multiple cameras at the same time. So the guy has done yeoman's work in terms of getting on. I mean, how many gigabytes of data do you have? It must be an enormous database of video that you got.
I got a big block of an archive, no doubt. But yeah, totally worthwhile. And you feel like you're doing something important, you stick to it.
Yeah, for sure. So I really appreciate it. But before we ever met you guys, or even before we even got Randall on our show to talk to him, I've been subscribed to GeoCosmicRex and been watching those videos. So it's been great to meet you. Basically.
Oh, thanks, guys.
Randall, get out of
here. Yep.
Well, and then we
finally, the stars align and things get moving forward. So we're happy this finally happened. We've been talking about it for years, and here we are.
Yep.
And so, and then November, we're all going to be at the Earth Keepers in Arkansas.
Earthkeepers / Atlantis.
I don't know their exact name of it, but yeah, it's coming up a week before Thanksgiving.
Yeah.
We'll be together out there.
Yeah, we'll be out there. That's going to be fun.
Oh, yeah.
What else? No, the RSS feed is up. So, and we're adding the shows. We're going to catch up to Brad. Brad's at 4 episodes up on YouTube, soon to be 5.
Yep.
We'll have 4 to 5 up.
Yeah, catching up to Brad is my job.
Yeah, that's this guy.
So basic computer science technology. I got this.
Yeah, so we're getting there. Also, thanks to everyone who is supporting the show through Patreon. We really appreciate all the Patreon supporters. Thank you guys so much. And keep sending us emails. Keep commenting on the YouTube videos. We love the comments. I read them all. Yeah. You guys, the vast majority of the comments are very positive. And, the guys that are, even the negative ones I laugh at because they're hilarious, like the shiny people. It's freaking hilarious.
They're laughable. Keep them coming. That's right. We read them all.
That's right. So I think that's it for this week's episode. That's episode 10, guys. We're in the double digits.
Yeah, nice. Beautiful, Randall.
Cranking out, yeah.
All right, Brad.
That's a good one.
All right.
Yeah, so I'm driving the clown car of co-hosts. Give me a mask. Yeah, it's awesome. It's fun. We appreciate it. And Randall, we're getting it out there. So it's exciting to be doing this with you.
Yep.
Likewise, boys. All right.
This is Kosmographia, the Randall Carlson podcast.
Is it next week we're not doing it, or the week after?
It's next week. We're off.
Okay.
Yeah.
Yep.
So see you guys in 2 weeks.
Episode 11 coming soon. Nobody else will know the difference.
Yeah. No one else. They won't know because we've got
right.
a backlog. So.
I was like, is it show 9? You just said show 10.
I know, he's like, so here we are for episode 9.
All right. Well, we blew away the 45-minute time limit. Here we go. Good stuff. Good stuff.
I've already stopped the recording. So
Yeah, we already stopped. We're no longer recording. Yeah.
All right.
And Randall, I was going to ask you, there was a lot of joking around on that one. Sorry about that. We kind of pushed you off, and asking lots of questions. We pushed you off track. So
no, that's fine. No problem.
Okay. Cool. Yeah. Sometimes I need to ask questions, and I'm like,
sure.
Ask this, and I know it's going to turn into a 20-minute conversation.
Look, like some of those videos that Brad, from older days, when you've got a crowd of 30 people and half a dozen of them are constantly interrupting and asking questions and making comments. No. Yeah. So that, I was almost used to that kind of stuff.
Right. Yeah. I have watched some of those. Yeah.
Yeah. Constantly fielding this stuff.
Yep.
So yeah, compared to that, no, it's no problem.
Exactly. Yeah, really.
All right. Well, man,
I thought it was a fantastic
great episode.
Superb. Yeah. Oh, absolutely.
Dude, you
good transition out.
You answered one of the big things that I have been trying to understand that you've been talking about in since we started the podcast, was the idea from the very beginning about the isostasy actually possibly causing this longitudinal motion of the crust. And I was just like, why would it? The way you explained it this time I got it, and you were like, I'm doing a terrible job of explaining it. That's what I need. The way you just explained it.
Kyle needs the terrible job.
So yeah, I totally got it. And I'm gonna have to think about that because, yeah, I don't know. There's a lot of
layers, definitely layers going on there.
What's involved in that?
Yeah,
in that
I also like the idea that vertical movement can change the plasticity, and that will make it easier for.
Well, it definitely changes the viscosity, which will change the plasticity.
That's what I'm talking
about.
The viscosity.
Words?
No, I'm agreeing with you and saying that. Yeah, that's going to happen. Right. But anyway, that was fascinating.
Yeah, it was a great show.
Loved it. I'll let you guys go.
Yeah, great show. You got a dog.
Right,
you got a fuzzy dog there.
Yeah.
And mine?
Yeah, right behind you there. So
you can actually see him.
Well, I saw a fuzzball.
Yeah, we saw a fuzz butt.
Otis.
Yeah, I was gonna say that's got to be Otis, really.
Yeah, there's
Look
fuzz
at that
butt.
wide body, Jesus.
Yeah, Otis. He's like a double wide trailer with fur.
It's a Sherman tank.
Look at that guy. Hello, Otis.
Gentle
good
giant.
Old dog.
Gentle giant. Hey, Otis. All right, guys.
He's a gentle giant.
All right.
All right.
Randall, I'll be down there. Talk to you Friday, probably.
Okay, good. All right.
Bud.
Well, I may talk to you. I'll probably try to see Wilbur tomorrow because I'll miss next week. But
Yep.
Yeah. So I may have some more thoughts on how we're going to actually, probably like I was telling you the other night when we talked.
Well, yeah, I might just call you when I'm driving down then.
Okay.
See if I can catch you.
Next week, just tell us why your anus is like this. Good night, boys.
All right. Good night.
Later, gents.